Can computers really understand humans? Probably not, at least in the literal sense, but what would it take them to be able to communicate with us as we do with others? Do they really need to understand us in order to make us feel certain ways, or even change the way we did feel about certain things? This idea of computer inferred knowledge told with me in the past few months. Could an unfeeling device really understand aspects about us that can only be deduced through implicit communication? So I pondered on this thought and wanted to play on the idea of quantifying the extent that technology could understand our behavior or personality through manipulation to eventually alter a personal bias. Ultimately, today I want to present a program that can infer communication implicitly and weigh the accuracy of it. So I want to first explain the theory behind the programming relating to what we're going to be doing. So a database is like a table stored in memory that holds information relational to one another. This means that there are predetermined relationships between the collections stored. For example, I can have a database of books where one column stores author, the other name, and one publisher. In this case, the book is relational to the author, name, and publisher. Suppose the name X is requested from code, and there are two books corresponding to the same author. Which book should be accessed, and how should they be differentiated? Well, we can add a unique book ID for each book of an author, where instead of filtering based on author, we can retrieve data relational to an ID. This ensures that there is only one of each book ID, so in every query, only one result is accessed. So this is basically the steps to our program, where I'll take a corpus of human inputted data from an interface and inject it into the code, where it will be stored into databases and analyzed. However, first let's consider the data being collected itself. This is a small sample of a feed where the human is communicating emotion or rationality to the computer. For example, in one card there is an image of the Wall Street Bull. As this could be a sensitive topic, there are a multitude of varying underlying options that the user can input as reaction. This appearance is somewhat alike to a Facebook or Instagram page by design, as it minimizes friction to answering a question. This is because images evoke emotions without having to be processed by imagination. As if I simply put Wall Street Bull as a text and gave the same responses underneath, I cannot really control what the person imagines as the Wall Street Bull. Thus, providing an image gives the ability to handpick stimuli and in theory only get responses for that specific one. So getting a bit into the program, here is the table storing the questions to any given feed. As you can see, there can be numerous feeds that are differentiated by quiz name. In this table, the unique ID represents the question, which is then linked to the answer table. In this table, an answer is related to the question through the question ID, which is the same ID in the questions table, which means that a question can have unlimited answers differentiated by their unique answer ID. Another column in this table is used as a machine learning prediction model for the program and can learn in time. For example, if there is a question X and it has responses A, B, and C, there are weightages or likelihoods related to that question that are given in percentages, meaning that they add up to 100. So if, for example, blue in the first row is chosen, there is a derived 80% chance that the inputter was, let's presumptuously say, male, in a quiz which is trying to find the percentage of males in a sample size. Whilst there is only a 20% chance of being male if the color chosen was pink, again, very presumptuously. Furthermore, because there are numerous questions for each feed, a created formula was used to derive an overall likeliness for implicit inference. In this formula, calculation is done by taking the average weightage for each inputted answer. Enabling the computer to download the data from the cloud requires knowledge into the Google APIs. So first we go into developer Google console settings and create an OAuth API key, which will allow the computer to enter the cloud using my credentials without major involvement on my part. This is seen over here, where the API key is registered to my specific code. Now we must add Google dependencies for client secrets, OAuth, API, and Jackson into the code, which will provide objects that can be used specifically to retrieve content from the cloud. This is done in 3 major steps. First, we download the credentials.json file from the Google cloud and put it as a dependency into the program. This is the credentials.json file, which basically holds essential information to log into Google. Second, the credentials are used to get a sheet service that allows scripts such as this Java program to retrieve, modify, and access Google Cloud spreadsheets. This is seen in this step over here, and this step over here. Third, a response is created where the code asks for all items in the cloud and gets an array of objects containing the data. This is seen over here, where the code retrieves a list of objects with the values inside the database. Google knows which spreadsheet data to give using a unique spreadsheet ID over here. This is similar to the concepts discussed earlier, where a unique ID correlates to the spreadsheet that we need to access. Now I want to show the program running and at which specific times the program adds things into databases and when and how it calculates the prediction. We can visualize this through the debugging menu, which is this button here. The program is starting up, loading through the code, and we should get the debugging menu shortly. In this step, the program has created 2 maps that we have already visually seen, one of them being the questions table and the other one being the answers table. We can, for example, see the questions table and the specific ID for each question. If I open up this menu over here, we can take the question, how do you feel, for example, and we can see that the unique ID is 10. Which correlates to what it is in the visual table. We also know that the quiz name is final, and this also shows up in the debugging menu. So from here we understand that in this line, up till here we've created a question map and we've added values into it. Moving to the next step, we're basically skipped forward to the point where the program has created another table called data collected. In this table, we are appending the values that we saw in this large database of responses and adding it into the code with their own respective unique IDs. We can already see that the prediction for this set of people is 29%. So tying this back to the original premise of the program, can computers really understand humans? Truth is that in the current state, we are training the machines to understand emotion, almost like a child when it is born. The more data or experiences that are collected, the better the predictions or emotional quotient can be. For example, the computer program that was created today stores previous results in another database table. As an extension to this program, this table can be used to tweak weightage and evolute on inferences. Ultimately, this journey has taught me that yes, indeed it is true that machine learning can to a quantifiable degree grasp human emotion, but it is only in the way that we train it to do so. Therefore, the discussion is no longer remaining about can they understand humans, but more about how much can we make computers understand us.